Hello, everybody. Good morning, or good evening, or good whenever it is that you happen to be watching this. And welcome to the Reach for the Stars webinar for the 2024 to 2025 Science Olympiad competition season. My name is Connor. I'll be doing the webinar with you today, and I hope that you find it very helpful and informative. This year, the focus of Reach for the Stars, which is our B Division space science event, is going to be on late-stage stellar evolution and stellar remnants. So, as always, we're very thankful to be sponsored by NASA's Universal Learning Program, as well as our partnerships with the Chandra X-ray Observatory, and of course, National Science Olympiad. You'll be able to check out all of these programs if you are interested in learning more or seeing some of the educational resources that they have for space science learning for students at all those links that are given below. And then, of course, this webinar, as in years past, is going to be posted to that link on the Chandra website over there on the top right. And you can find this webinar there once it's posted, as well as all of the others that have been recorded in years previously. So, as I said at the outset, this year the content focus for Reach for the Stars is going to be late stage stellar evolution and stellar remnants, which are the remnants left behind at the end of a star's life. We're going to be focusing on observing these objects and these late stage evolutionary processes for stars across the totality of the electromagnetic spectrum. So, this is at the highest energy at gamma radiation, going all the way out to the lowest energy, longest wavelength observations in radio wavelengths. And everything that falls in between is fair game for this year. So to talk a little bit about some of the red highlighting that you see here, everything that is highlighted in red as I go through the rules of the event this year, these represent changes made between last year's event and this year. Last year, Reach for the Stars was focused on early stage stellar evolution, pre-main sequence, which is before the state at which a star is burning hydrogen as the main fuel source in its core. Whereas now we are focusing on late stage, so this is everything that comes after the main sequence. And that's what the content focus is going to be for this year compared with last year. There's going to be a lot of overlap between last year and this year. Stellar evolution is, of course, a very broad topic, and the general trajectory of stars through their evolution is always on the table to some degree. But this year, the focus is on late stage stellar evolution, everything that happens in a star's life cycle after it transitions off of the main sequence. So to go a little bit over what some of the content and allowable resources for the event this year are, you have teams of 2 competitors. This is pretty typical for most study events that you see in Science Olympiad, and that's going to be the case here as well. A 50-minute long event, you'll have 50 minutes from start to finish if you're competing, and the event parameters allow you to bring 2 8.5 by 11 two-sided pages of information in any form from any source. So physically, 2 pieces of paper. Each side can be filled out, so you have 4 sides of a piece of paper, 1, 2, 3, 4, if you were counting page numbers in a book. 2 physical pages, double-sided. And you can have as much information or as little information all you want as you want on those two pages. So talking a little bit more about the competition this year, if you look at the rules, you'll see that participants may be asked to identify the constellations, star systems, and deep sky objects on the list below as they appear on star charts, HR diagrams, and photos taken in various wavelengths. So this is what we would call the deep sky objects or DSO portion of the event. Exams for this event are going to some degree, ask that students be familiar with questions related to these objects, and I've listed them all out here below. And you can see that all these are in red, which means all the objects this year are brand new. We've shortened the list down from where it was last year. I believe this year we are doing 1, 2, 3, 4, 5, 6, 12 objects, as opposed to what we had last year, which was more than 12. I think it was closer to 16, 17, 18. So we've cut down the number of objects. We want students to be very focused on a few very important objects that are very representative of what the topic for this year is going to be. Again, late stage stellar evolution. If you have any objects out there from previous years, they should not be included on this year's exams. This goes for test writers as well as for people who are studying. No exam should contain any detailed questions about specific objects that are not listed here. A question about red giants in general, totally fair game. A question specifically about the red giant Antares, not fair game. Should not be on there. questions must be broad. You can use specific other objects as example cases, as case studies in certain kinds of objects, but these should not be questions that actually cover these specific mechanisms, processes, or identification in images or on star charts or in HR diagrams, only for these 12 objects that are listed here. And I'm going to go into detail with each one of these later on in the webinar. So in addition, students may be asked to demonstrate their knowledge of late-stage stellar evolution by answering questions pertaining to the following topics. And I'm going to go through a couple of these right now. First one listed here is the structure, physical properties, and mechanisms of the following stages of post-main sequence stellar evolution and stellar remnants. So this is a carry-through from last year in terms of students having familiarity with structures and physical properties. What is it actually like when a star evolves off of the main sequence and into different paths of evolution based on its mass? I'll get into that a little bit later. And I've listed out what these are right here. So the stages of stellar evolution that we want students to be concerned with the structural and physical properties of, as well as their mechanisms and how they are identified, are the red giant branch, the asymptotic giant branch, planetary nebulas, white dwarfs, all types and subtypes of supernova, neutron stars, pulsars, and black holes. Additionally, we want students to be familiar with orbits, behaviors, and potential evolution, things like mass transfer or decaying orbits, of objects in compact binaries. And we've listed out a couple different kinds of compact binaries. These are examples. This is not a comprehensive list. But for example, compact binaries can take the forms of novae, of X-ray binaries, of neutron star binaries, or black hole binaries. There are other possibilities that we want students to be familiar with. These are just a few possibilities, as well as a few potential mechanisms of how these compact binaries might evolve. Next topic is observation and classification systems of post-main sequence stars. So again, that is late stage post-main sequence, as well as stellar remnants according to their spectra, light curves, and physical parameters, such as, but not limited to, temperature, luminosity, and mass. So these are where your mathematics and classification questions come into play, which I'll talk a little bit about later. And these are the kinds of questions where we want students to be focusing on how do the physical properties of stars off of the main sequence or in their stellar remnant phase interact with one another and produce changes. And how do we track and classify those changes? How do we classify stars based on their spectral class? How do we classify them based on mass, temperature, distribution of elements in their photosphere, the way that they vary in brightness over time, that sort of thing. We also want to extend into the next section the engineering and design principles associated with the following listed observatories. So we want students to be familiar with how these observatories are used to conduct science, what aspects of their engineering, their orbital design, the way that they were physically built enables them to do science. And the only instruments that we want students to be concerned with understanding these components of are JWST, or the James Webb Space Telescope, launched in 2021, Hubble, or the Hubble Space Telescope, which is currently operating, has been in operation for over 30 years. Spitzer, which was an infrared telescope that has been decommissioned. Chandra, which is an X-ray observatory, also still operational. Swift, Fermi, and LIGO are three new observatories this year. Swift and Fermi are both high-energy space telescopes, and LIGO is a ground-based gravitational wave observatory. It has two different locations, one in Washington and one in Louisiana, and it is the only one of these observatories that is not in space doing science in orbit. It is located on ground on the Earth's surface. And I'll talk about those more as well later on. And then finally, the last thing that I want to cover within this section is that students should have a basic algebraic understanding of the following concepts using order of magnitude estimation, proportions, scaling relations, and things such as that in order to demonstrate some degree of algebraic understanding of the physical processes that take place inside of stars. I want to emphasize that exams should not include any questions that require a calculator. I'll say that again. If you are writing an exam, Your exam should not require that your students have access to a calculator. Students should not be doing calculations. Students should not be prepared to enter numbers into something where they would not be able to very easily do order of magnitude estimations or doubling or having quantities in their head. Anything more advanced than that requires a calculator to any degree should not be on your exam. If a middle schooler is not able to do it without a calculator, it should not be in there. You'll notice that I didn't list calculators as an allowed thing to be brought into the event, only your 2 sheets, 8.5 by 11 pieces of paper, and that's for a reason. We don't want anything more complicated than that. Okay, so what are the 3 things that we want students to be focusing on? The first is the relationship between stellar temperature, radius, and luminosity, also known as the Stefan-Boltzmann law, and I'll get on all of this later in the webinar as well. We want students to be familiar with magnitude, luminosity, and distance scales, including, and this is new, period luminosity relations and standard candles. So these are ways of measuring the distances to stars based on what we observe about them from Earth. Some of this is a carryover from last year, and some of it is new, the period luminosity stuff and the standard candle stuff. Standard candles are objects that have a consistent absolute magnitude, and thus, if you can detect how bright they are from the Earth with your naked eye, you can make estimations about their distance. I'll talk about all that later as well. And then the last thing, this has changed a little bit from last year, is we want students to be familiar with the principles governing orbital mechanics and gravitation, such as, but not limited to, Newton's laws of universal gravitation, Kepler's 3 laws, how Schwarzschild radii are calculated for black holes, how binary systems can be constructed and how they tend to follow Newton's laws of gravitation, Kepler's laws, that sort of thing. But this is a broad topic that covers how orbital mechanics and gravitation cause objects to interact with one another in space. Okay, so let's talk a little bit more detail about the content of this year's event. I'm going to start with stellar evolution. So this is a holdover from last year. This is a consistent aspect of the event, and students, whether you've competed in the event before or if you're brand new, this is something that you should always be focusing on, you should always be studying. Now, this year, we're taking a focus on stellar evolution as it pertains to late stages of stars' life cycles. This is everything after the main sequence. And remember, as I described before, the main sequence is defined by the time period of a star's life where it is creating energy inside of its core by fusing atoms of hydrogen. The energy that it produces by this pushes outward, and it enables the star to push out against the gravity that has, all of the mass of the star exerts gravity, and it wants to pull and contract itself inward. So stars like our sun, which is on the main sequence right now, it's about 4.5 billion years into its main sequence evolution, and it will stay on the main sequence for another 4.5-ish billion years, the majority of the life cycle of the star. So the main sequence is a relatively stable time in a star's life where it is burning hydrogen, and then the topic of focus for this year is everything that comes after the main sequence. So this is defined by the point where the star is no longer primarily supporting itself against its own gravity by the fusing of hydrogen in its core. There are a couple ways that we track where a star is in its life cycle, where it's going to go, and where it's going to end up. Over here on the top left, we have an HR diagram, which in this case is a snapshot of a whole bunch of stars in a cluster. Each one of those dots is one star, and it is a plot of a star's temperature versus its luminosity, or temperature versus absolute magnitude, spectral class versus luminosity. You'll see that each one of the axes is labeled in 2 different ways. And you'll see that the majority of stars fall into a string that goes from the top left of the chart all the way down to the bottom right. That's the main sequence. Most stars in the universe are currently on the main sequence because most stars spend most of their life in the main sequence. And of course, you should be familiar with what's happening during the main sequence, but that is not the main focus for this year. The thing that makes this event different and interesting this year is going to be covering of everything that happens after the main sequence. This is going to be everything that takes you through your red giant, your red supergiant, the asymptotic branch, if you're a small mass star, a planetary nebula and a white dwarf, and if you're a large mass star, a supernova and either a black hole or a neutron star. And the branching of those different pathways, depending on the mass of the star, are visible over there on that bottom diagram, which shows over time how do stars of different masses tend to evolve. And you'll see that the lower mass stars tend to evolve towards planetary nebulas, towards white dwarfs. Higher mass stars evolve towards supernovas on the low end, followed by a neutron star, and then on the high end, followed by a black hole. And then all of them eject matter back out into the universe, and then the cycle starts all over again when that matter recondenses into stars later on. So I want to talk a little bit more about how the post-main sequence is largely stratified by the initial mass of your star, and then the subsequent evolutionary tracks that come from that. So you'll see over here, I have a couple of different diagrams show up that explain a little bit about how the post-main sequence evolution is altered by the mass of the star. If you have a very high mass star, then you are going to see that the forces that operate to keep its gravity balanced against the pressure it can exert by burning elements inside of its core, and by burning, I mean fusing them together, nuclear fusion. That gravity is a greater force, and generally produces more spectacular outcomes at the end of a star's life, let's say. You'll see over here that there are a couple different mechanisms by which stars can die, to put it bluntly. And the death of a star in a high mass star, as I said, usually a supernova, and the death of a star in a low mass star, usually a planetary nebula. There's simply not enough mass in a low mass star for it to have the kind of core collapse process that defines supernova. You need to have more mass, you need to have more potential gravitational energy collapsing in all at once. Instead, a low mass star, like our sun, is going to die via a planetary nebula, where it sheds off its outer layers, and all that remains is the white dwarf, which was there at the core of what is left of the star. You get the planetary nebula, which is a very bright and beautiful looking collection of gas and dust with a whole bunch of different elements in it, and that surrounds your white dwarf. And that's what happens when you don't have enough mass to go into your supernova stage. When you do have enough mass to go into your supernova stage, as the star is no longer able to support itself via nuclear fusion, it collapses in, and the gravitational force, because there is so much mass present, is strong enough that it will rebound in what we call a core collapse supernova and leave behind either a neutron star at the lower end, or if there is so much mass, it will actually go down into a singularity, produce a event horizon, and we call that a black hole. That is when you have enough mass that you are able to contract everything down gravitationally, no longer supported by the outward pressure, and you become a black hole. Ordinarily, you do still have supernovas in this instance. There is a rebound that ejects material back out, but black holes are on the higher end of masses for stars. And then over there on the bottom, I have a demonstration of how two different kinds of supernovas can happen. Type 1 supernovas are produced by binary star systems, where one star achieves the high mass state necessary for a supernova to take place by accreting mass or having a gravitational pull suck some of the mass off of a different star that is orbiting around it, or that they are orbiting around each other. And that mass falls onto the first star. It gains enough mass that it can then undergo that supernova process. We call that a type 1 supernova. And then a type 2 supernova occurs when all the mass is there in the one star to begin with. It no longer supports itself, and it collapses and then rebounds in a big supernova explosion. And that is what I was referring to at the onset here. Something else we want students to be familiar with is constellations and star charts. I'm going to talk a little bit about identification of different objects. One of the ways that you do that is by looking at dislocation in the night sky. So you'll notice that I laid out the constellations for each star or object in the beginning of the DSO section when I went over the rules. And that's because we want students to be familiar with the constellations that these objects are in. Now, in almost every instance, we just gave the one constellation for the one object. We were trying to simplify a little bit this year, but there was one instance, the constellation Cygnus, where we have two objects that are being present in one constellation. I'll go over both of those objects. They were chosen because they're both extremely important objects in the context of late-stage stellar evolution, and we want students to be familiar with both. But largely speaking, if you know what constellation the object is in, you should be able to know which object you are looking at, and vice versa. That's how we set it up this year. So you'll want to be familiar with where constellations are relative to each other, as well as which hemispheres those constellations are in, and very importantly, where within those constellations are the objects located. So speaking a little bit more about these objects, I've broken down the objects that we have for this year into a couple rough categories. Some of these objects have overlap between the categories, and some of them within a category are pretty substantially different from one another because classification in astronomy can be kind of fuzzy. But broadly speaking, you're looking at two different kinds of objects that are being studied for the competition this year. First one is stars and star systems. So these are just individual stars or stars in a binary system. So you have Sirius, the star Mira, you have the star Aura Lyrae, and you have the star Betelgeuse. And then we also have stellar remnants. So these are not necessarily stars, but they are things left behind after a star undergoes that process of dying, no longer being able to burn anything in its core to support itself against its own gravity. And so the ones that we're going to go over here, and I'm going to go one by one through them after this, is the Holst-Taylor pulsar. We have Cassiopeia A, Cygnus X1, SS Cygni. Those are the two that are both in Cygnus, Cygnus X1 and SS Cygni. SN 1987A, SN stands for supernova, NGC 6543, and SN 1604. And there's one last object that we're including this year, which is kind of hard to fit into either one of these categories, which is GW 150914. GW stands for gravitational wave. So GW 150914 is the name of a gravitational wave signal that was detected by the LIGO Observatory. That's the one that's on the ground with two different locations, the one that I talked about earlier. And this one's in the other category because it's less of an object and more of a signal that was detected. There were objects that went along with this signal, and we want students to be familiar with the objects that produce this signal, but the signal itself is what's being covered by the rules this year, so it's in that other category. Okay, let's talk a little bit more about these objects in particular. So the first one that we have here, and I'm going to be going alphabetically through their constellations, so you'll see up there, if I can move my finger, right above me, I'm going to have images of constellations as well as a red circle that indicates where this particular object is within that constellation. So the first one in the constellation of Aquila is the object, the Holst-Taylor pulsar. This is a stellar remnant, and it's a binary pulsar, which means it's two objects in orbit around each other that produce the pulsar effect, which consists of a neutron star and a pulsar. The way that pulsars work is that they radiate out from a bipolar location, so two opposite sides of the remnant neutron star. Pulsars are a type of neutron star. They radiate out kind of like a lighthouse, these beams of very high energy light that when they cross the path of the Earth as we observe them, they will appear to blink and they will pulse to the Earth. And that pulse, as the star rotates or goes around in an orbit, is what leads to us calling it a pulsar. And this is a binary pulsar where you have the one pulsar that is orbiting, and then it has a common center of mass where another object, a neutron star that is not a pulsar, is also orbiting. So they're in a binary system. And as they move in this binary system, they are observed to have what we call orbital decay going on, which is to say that the orbit, the distance separating the two, is shortening over time. And they are orbiting closer and closer and closer. So we are seeing changes in how quickly they orbit. We are seeing changes in the separation between the two objects. And this is the first instance of this ever being discovered. Now, because of this, we were able to look at the gravitational waves produced by such an event, and this actually lines up with the general theory of relativity precisely. So Einstein has a general theory of relativity, and that is a means of describing the way that we would expect gravitational waves to be produced by objects in a decaying orbit, among many other things. And because this was the first object of its kind ever discovered, the Holst-Taylor pulsar is really notable for acting as a confirmation of the general theory of relativity. The next object on our list is the star Sirius, which is in the constellation Canis Major. And Sirius is a star system. Sirius is a star system of two different stars. The first one is Sirius A, which is a A-type star. That's the extremely bright star there in the center of that image on the left. And then also a white dwarf star. which if you look at this image on the left, in the bottom left-hand corner, there is a tiny little dot of light. There is the enormous, big, bright ball of light right in the center with kind of the X going through it. And there is the tiny little object that is down there in the lower left-hand corner. That tiny little speck of light is Sirius B, which is a white dwarf star. So here we have an A-type star and a white dwarf, which are in orbit around each other. Sirius A, of course, is notable. You may not already know this for being the brightest star in the night sky. If you look out if you're in the northern hemisphere and you look out and you're looking at the constellation Canis Major, you'll see Sirius as this extremely bright, extremely visible point of light. It's the brightest star in terms of visible magnitude, or the magnitude that we can see with our naked eye in the night sky. And so it's been a basis for people who navigate or plan their calendars or any aspect of their society via the stars pretty much throughout all of history. It has always been one of, or basically the brightest star in the night sky, not counting our sun. And as a result, it has been highly visible throughout pretty much the entirety of human civilization. So it's very important in a lot of cultures and a lot of ancient and pre-modern and honestly still modern history for its use as a means of navigation in the night sky. And Sirius B is interesting because being such a tiny star drowned out by the light of the other star that it orbits around, it is not possible to see it with your naked eye if you were sitting here on Earth. You can see it with very, very powerful and very precise telescopes, and you can detect it if you're looking at its gravitational influence within the Sirius system. Sirius B is a very well-studied white dwarf. It was one of the first ones ever discovered, the second one ever discovered. And as a result, it's been studied for a very, very long time. It is a very well-known, very easily visible, and very easily studied object. So we've learned a lot about what we know about white dwarfs from studying Sirius B. Next object on the list is another stellar remnant. This one's called Cassiopeia A in the constellation of Cassiopeia. And Cassiopeia A is the remnant of a type 2b supernova, one of the first to ever be observed. So type 2 supernovas, and remember we have different subclasses of both type 1 and type 2 supernovas. A type 2b supernova is the kind of supernova that was produced in Cassiopeia A. And it is very famous for a lot of reasons. It's a very easy object to study because it is so bright, especially in radio wavelengths. In fact, it's the brightest radio wavelength in the night sky that is not within our solar system, which also makes it one of the most well-studied supernova remnants. There are a lot of images of this object. That one over there on the left was taken by JWST in combination with other types of data. You can see that there is some blue and green in there. Those are X-rays. Some of the orange and red is taken by JWST in the infrared. And then over there on the right, you can see images of that stellar remnant in a whole bunch of different wavelengths that demonstrate the distribution of elements and material and sources of light within the object. So Cassiopeia A is a very well-known and well-studied object because of how studyable it is and because of how much there is to learn from applying different methods of observation with different observatories. And I want to make a correction. I think I said by accident on that left-hand image that the orange and red is JWST. It is not. That is Spitzer data. Spitzer is an infrared telescope that is no longer operational. So the next object to talk about is the star system Mira, which is in the constellation of Cetus, the whale. So Mira is a star system, again, similar to Sirius. It's a binary system of an A-type star, Mira A, and its white dwarf, which is Mira B. Now, the A-type Mira A is a very, very well-studied variable star, which means that it is a star that varies in brightness over some predictable period of brighter, and then it'll become dimmer, and then it'll become brighter, and it'll become dimmer, and it goes through that cycle over very rare, and then it gets bright, and then it gets dim. And by observing it over a long period of time, we can learn about the star and look at other stars that are like it to understand more about this variable process. It's probably the first non-supernova variable star ever to be discovered. It's been observed for a very, very long time, and it's the prototype of a certain class of pulsating variable stars. These are called long-period variable stars. These are stars that have a period on the order of 100 days or longer. Some stars have very short variable periods, maybe only a couple days to maybe a week or so. Myra is a long period variable star. It's a very long period. In fact, Myra's light curve, if you are able to see very closely down there, and if you are good at reading Julian dates, you'll see that it has a 332-day long period. So it takes almost a full year for Myra to go through its complete cycle of bright to dim and then back to bright again. And that's over there on the right-hand side. And that's what we would call a light curve. Light curves are very useful as means of identification. Stars that vary in similar ways are going to have similar light curves, and Myra is a very classic example of one such star. Next object to go over is Cygnus X1 in the constellation of course, Cygnus. Cygnus X1 is a stellar remnant. It is an X-ray binary system with a blue supergiant variable and a black hole. Over there on the left-hand side, there is a artist's representation of what this system would look like. You can see that blue supergiant there on the left, and then you can see the black hole there on the right. It's that tiny little dot inside the big disk of very hot material. And you'll see that in this artist's representation, what's being drawn here is the process of the blue supergiant having all of the mass in the outermost layers of itself pulled in by the black hole and spiraling into this disk. Now, this disk gets very, very hot. It starts to glow in X-ray or even more intense light. And that is one of the ways that we've discovered Cygnus X1, by observing it in X-ray. In fact, it's probably the most well-studied X-ray source in the night sky, or it's one of them. And it was the first of its kind to be recognized as a black hole. This was an ongoing debate between some astronomers for a long time. Two very famous physicists, Stephen Hawking and Kip Thorne, had a bet about what kind of object it was. And after study revealed that it was a black hole and not some other means of producing X-ray phenomena, as Stephen Hawking thought, Kip Thorne won that bet. Got to say that he proved Stephen Hawking wrong, which is a pretty cool little feather to add to your cap as a physicist. And it's a very well-studied object for exactly this reason. It was discovered very early on in our understanding of how black hole X-ray binary systems could function. And as a result, studying it can tell us a lot about how these systems evolve and change and behave over time. Next object, also in the constellation of Cygnus. So this is a stellar remnant similar to Cygnus X1, but not quite the same. It's a binary system of a red dwarf star and a white dwarf star. So Cygnus X1 was a large blue supergiant star and a black hole. SS Cygni is a red dwarf and a white dwarf, so both lower mass and both very different points within a star's life cycle, dictated by, in the case of a black hole versus a white dwarf, different trajectories based on your initial mass. Remember, white dwarfs are the result of low mass stars dying, and black holes are the result of high mass stars dying. And this is a similar setup to what's going on with Cygnus X1. You have the red dwarf that is having matter pulled off of it by the gravitational influence of the white dwarf. But rather than producing these consistent X-ray glows that you see in Cygnus X1, we see that SS Cygni regularly brightens and dims from material that falls onto the surface of the white dwarf. So as material falls in, it causes the white dwarf to have matter accrete onto its surface, and then that is the thing that actually causes the brightening. It's this big reaction of a whole bunch of matter. It creates this photon and energy push out that halts some of the process of material falling in, and so then it dims again, and then it gets more material back onto it. As it dims, material is able to fall back on again, and then it brightens up again, and then this cycle repeats. You can see over there on the right-hand side a very long-term light curve of SS Cygni that was captured by amateur astronomers. And SS Cygni is notable for having two different period lengths. It can undergo short 12-day periods where it's shaped like an S, where there are only 12 days between outbursts. And then can also have greater than 12-day long outbursts. Sometimes these last a couple weeks or more in these kind of L shapes in the light curve. So you have your short and your long periods in SS Cygni. Next object to go over is SN 1987A, or supernova 1987. This 1987 designation is an indication that this supernova was observed first in 1987. So this is one of the first modern supernova to be observed, definitely the first one to be studied as deeply as it has been. It's a stellar remnant. It is the result of a Type 2 supernova, which is the same kind of Type 2 supernova that we saw in Cassiopeia A. Type 2, of course, as you remember, being the core collapse scenario where the mass of a star is so great that it collapses in upon itself, and then you have a supernova event just from that one star. So supernova 1987A is really notable because it is relatively nearby, and it is one of the first supernova that happened at a close enough distance in the modern era for us to study it using modern astrophysical tools, namely telescopes that exist in space, not blocked by any of the atmospheric interference that you see in the atmosphere if you're doing ground-based observations. We've had a lot of insights into the nature and behavior of core collapse supernovae as a result of studying this object. Over there on the left-hand side is a Hubble image of the supernova evolving over time. And then over there on the right, you have the light curve of the supernova. Note that there's a very bright initial light spike. That was the supernova event itself. And then over time, it tapers off into a more stable period of lower but still very intense brightness. Next object to focus on is NGC 6543, which is in the constellation of Draco. This is another stellar remnant. It is a planetary nebula, and it was the first to have its spectrum, or the elements inside of it, analyzed. The spectrum, I'm sorry, I should say, in more precise words, the spectrum is an analysis of the light coming from the object that shows characteristic fingerprints of where elements are and what elements are present. And I'll go into spectral analysis a little bit later on. So the Cat's Eye Nebula is another name for this object. NGC 6543 has been nicknamed the Cat's Eye Nebula because if you look at it, it kind of looks like the eye of a cat. And it's one of the more well-studied planetary nebulae in our solar system. Sorry, in the night sky, not in the solar system. Definitely not in the solar system. One of the most well-studied planetary nebulae in the night sky. And remember that planetary nebulae are a type of stellar remnant that is produced when a star of approximately the mass of the sun, or maybe a little bit greater, or maybe a little bit less, has its stellar death cycle where it sheds off its outer layers and a white dwarf remains. It's one of the most well-studied examples of this, and it demonstrates the stellar nature of these nebulas through its spectral analysis. Before we had a chance to actually look at the spectra of planetary nebulas, they were thought to be something entirely divorced from the process of stellar evolution. They were kind of thought to be their own thing, but we now understand them to be the end result of stars of around the mass of the sun dying because of looking at the spectrum of this object and others like it. The next object to talk about is the star RR Lyrae. So this is just a single individual star, and similar to Mira, it is a variable star, which means that its brightness increases and decreases over a predictable time period. But it's different from Mira in that it is a shorter period variable star. In fact, it's the prototype of an entire class of variable stars that show intrinsically driven pulsating variability. What this means is that the variability of the star is driven entirely by this pulsating process that happens in the star itself. The star will expand a little bit, and then it will grow brighter and then dimmer, and then it'll contract. And as it contracts, it will start out dim and then grow bright again. As material is squeezed into itself, it'll heat up. And then it will expand out again. The thermal pressure will push it outward again, and then it starts to dim, and then it will contract, and it'll go through that process over and over and over again. So you see over there on the left-hand side is an HR diagram positioning of where RR Lyrae variable stars tend to be. And over there on the right is what the light curve of these types of stars would look like. And RR Lyrae variables are especially notable because they are a type of standard candle, like I alluded to before, and they have very regular period luminosity relations, which means that if you look at the period of the star, it's very consistent, and you can determine the luminosity of the object because it's directly related to its period. So if you have the luminosity as a known set value, then that makes it ideal for measuring cosmic distances due to the distance modulus calculations that I'll go into a little bit later, that enable you to understand how far away a star is if you know how bright it is intrinsically and also how bright it appears to our eyes from Earth. So RR Lyrae is a prototype of this kind of object, and it is one of the more well-studied examples of one. SN 1604 is another stellar remnant in the constellation of Ophiuchus. It is a very well-studied remnant of a type 1a supernova. So remember, type 1 supernovas I went over before are the ones that accrete matter onto themselves and then undergo their supernova event because they've accumulated so much mass that they collapse and have a supernova. So it is one of the most recent visually observed supernova, which is in the Milky Way. That 1604 designation is, similar to SN 1987A. This one was observed in 1604. It was observed by Johann Kepler in 1604, and thus it's sometimes also called Kepler's supernova remnant, or SNR. That's what SNR stands for, supernova remnant. And it is one of the most well-studied examples of a type 1a supernova. We have learned a lot about how type 1a supernovas evolve over time and what kind of processes dictate their formation and production as a result of studying SN 1604. Next object that I want to talk about is Betelgeuse, which is in the constellation of Orion. Betelgeuse is a very famous star, maybe one of the most famous. It is one of the brightest and most easily identifiable stars in the night sky. It appears as a very bright, deep red star in the shoulder of the constellation Orion. It's very easy to see, especially during the wintertime. So if you were watching this webinar when it comes out in the fall of 2024, September, October timeframe, start watching the night sky and start seeing if you can find Orion, the constellation, coming up, because it's a wintertime constellation if you're in the northern hemisphere. And it is one of the most easily identifiable stars during the wintertime in that constellation. So it's been studied for a very long time. We have records of at least the ancient Greeks studying and writing about Betelgeuse. And that has informed our understanding of red supergiants and semi-regular variables, Myra and RR Lyrae. Remember the two stars that I talked about that show variability, one over a long period of time, one over a short period of time, but both of them doing so regularly, very predictable periods. Betelgeuse is less regular. It is a semi-regular variable. It does show fluctuations in brightness, but it's a lot less stable due to being a red supergiant. Red supergiants are just less luminously stable stars than other types of variable stars. And you can even see there over on the right-hand side a light curve of Betelgeuse. You may remember that in about late 2019, early 2020, there was this very interesting dimming effect that was happening in Betelgeuse, and it was theorized, although never very seriously expected, that this could be the indication of Betelgeuse approaching a supernova event, because very, very, very giant stars at the end of their lifetime will sometimes undergo this dimming period before they undergo their supernova events. That did not happen. It was just a part of the semi-regular and sometimes irregular variability that we see in Betelgeuse over time. But you can see that that is represented by that big dip downward right in the middle of that light curve on the right-hand side. And the last object that I would like to cover with you today is not so much an object as it is a signal. This is what I alluded to before. This is GW 150914. The GW here stands for gravitational wave, and the 150914 is the date, 2015, September 14th, September being the 9th month of the year. That is the date that it was verified as an event produced as a gravitational wave signal by the coalescence, the spiraling in and then merging of two black holes. So over there on the left-hand side is an example of those two black holes orbiting around each other. Unfortunately, it doesn't look like the animation is playing properly, but what is happening here is you have two black holes that are orbiting around each other, and as they do, they produce gravitational waves. And these gravitational waves were a core assumption of general relativity. Remember when we talked all the way back with the whole stellar pulsar about general relativity? This is another example of it being confirmed. And the reason why this event in particular was so important and why this signal was so important was because it was a verification of this core assumption that two black holes, or two extremely massive objects in orbit with one another, as they move, would produce this gravitational wave ripple effect in space-time. So the observation of this ripple as a signal called GW 150914 was a space-time event that confirmed this core assumption of general relativity. It was a very important discovery in the history of gravitational physics and in how we understand our universe. Okay, So those were all of the different objects that we want you to be familiar with as competitors this year. I'm now going to take some time and go a little bit through other physical principles and core aspects of the general knowledge of this event. I wanted to take some time to go into the objects in some degree of detail, and some of this is going to be repeated from what I covered there, but I'm just going to go through some of the other things that are mentioned in that section of the rules quickly, and then we will close out this webinar. So one of the most important concepts to understand in terms of what keeps stars physically alive, what is physically happening inside of the star that causes it to behave the way it does. A lot of this should all be understood in the context of nuclear fusion. And nuclear fusion here refers to two nuclei, oftentimes, at least on the main sequence, two hydrogen atoms that are physically being fused together. The core of a star is so hot and so energetic and so dense that atoms are fused together into new elements. If you take a proton and you fuse them together, in this case, proton and a proton being two hydrogen atoms that have been stripped of their one electron because it's so hot, you combine them together and you end up with helium. Because when you have two protons stuck together in one nucleus, that is helium. And after you've fused enough hydrogen into helium, you'll start to fuse that helium together. You'll take a helium and helium, stick those together, and take what is left of that and continue fusing them together until you end up with higher and higher proton numbers of elements. There are a couple different ways that this occurs. The three main ones to consider are proton-proton fusion, what I just described before. There is a CNO cycle for high mass stars, which stands for the carbon, nitrogen, oxygen cycle of bringing in different elements to fuse them together into higher mass elements in stars. And then the triple alpha process, which is for fusion beyond the main sequence. And I would encourage you to look into all of these on your own time. And then the other big idea that I want to go into a little bit more detail about is this idea of hydrostatic equilibrium. And that's a very scary sounding term because both of those words sound very intense and physicsy, but the process itself is actually not that complicated. When you have a very massive object like a star, many times the mass of the Earth, which is already, humongously massive. Anytime you take that much mass and you gather it in one point in space, it is going to exert an extremely high degree of gravity. And the gravitational influence of a star can cause it to not want to stay in its current shape. If you have enough mass and enough gravity in one place, it's going to want to contract in on itself. You have so much mass that all the gravity is kind of pulling it together. This is just an aspect of how the universe works. Now, if there was nothing else to balance against this inward gravitational force, then stars would just collapse as soon as they were born. And then we wouldn't have stars. We would just have a whole bunch of collapsed clouds of gas, and nothing in the universe would have the stars that support it. But because when you fuse elements together in the core of these very dense balls of gas that we call stars that are being contracted in by gravity, the fusion produces a expulsion of thermal energy, a really high degree of expulsion of energy. So great that we are here on Earth trying to capture it ourselves via nuclear fusion. In stars, nuclear fusion is happening all the time. It's happening in the sun right now as we speak. And the massive amount of energy that is released when you fuse two atoms together pushes outwards. We call this thermal pressure. And that thermal pressure pushes out against the force of gravity pulling a star in. So this is very important to keep in mind. The thing that causes stars to exist, to be able to continue existing, is directly a result of how much thermal pressure they can create against their own gravity by fusing elements in their core. And when stars are no longer able to do that by whatever mechanism, whether it's by burning hydrogen and turning it into helium, or fusing carbon, or fusing oxygen, or eventually getting all the way up to iron, then stars are no longer able to support the massive weight of gravity that bears down on them, and that is when we see stars die. They collapse, and if you have a low mass star, you get a white dwarf, a planetary nebula. High mass star, you get a neutron star or a black hole. Compact binary systems are another topic that we covered on this year's list, and I talked a little bit about these with the objects Cygnus X1 and SS Cygni, as well as the black hole binary that produced the GW 150914 signal and the whole stellar pulsar itself. All of these are examples of compact binary systems where at least one of the objects in the binary system is what we call a compact object. Compact objects generally refer to stellar remnants that are left behind as the result of a star dying, and they ordinarily mean white dwarfs, neutron stars, and then sometimes also pulsars, which are a type of neutron star, and black holes. These are compact objects. They are, relatively speaking, small in terms of volume, but extremely dense objects. There is a huge amount of mass packed into a very small space, and that's why we call them compact. And compact binaries can take a lot of different forms. They can be X-ray binaries, as was the case for Cygnus X1. They can be neutron star or black hole binaries, which was the case for the whole stellar pulsar and GW 150914. They can be a white dwarf with a red dwarf companion, as is the case for SS Cygni. Whole bunch of different combinations of compact objects, one or two of them in a binary system can produce these compact binaries. So there are a bunch of different types. Study all of the ones that exist and all the different combinations. You should be able to talk about what's the difference between two black holes in orbit around each other versus a black hole and a neutron star, or a neutron star and a supermassive red giant, or supermassive blue giant star, or a white dwarf with a red dwarf, a white dwarf with a black hole. All the different combinations, you should be able to describe physically what is going on in these systems and what might happen later, depending on what kinds of mass transfer or other processes we're seeing. Classification is very important in astronomy. Classification is how we delineate different types of objects that may otherwise appear similar. And we can do this in a lot of different ways. I've given 3 different examples of classification going on here. At the top left is the Harvard spectral class system, which is the classic OBAF GKM, O down to M being a spectrum of different very, very hot down to very, very cool stars. And these are spectral classes determined by the properties of the spectra of the stars. Again, a spectrum is a broad distribution of all the light coming from the star with specific parts of the spectrum blocked out by the presence of elements in the star's interior, or usually photosphere, that blocks out the light coming from the star. And then that will cause different elements to show up as a kind of fingerprint for the star. We also have the Yerkes luminosity class, which is a way of studying how luminous different stars are. So if you look over there on the right, going vertically, you have the different spectral types. That's the Harvard spectral class system. And then going relatively horizontally, but not perfectly, is the Yerkes luminosity class. Very, very luminous stars are over there at the top. Less luminous stars are down at the bottom. These are things like your dwarf stars, your white, red, and brown dwarfs. And you can see that stars can have different combinations of spectral type and Yerkes luminosity class. So something could be a luminosity class 0 star, a hypergiant, very, very luminous, but it could be an O type, it could be an F type, it could be an M type on the spectral class, and that is a measure not of its luminosity per se, but what elements are present in its spectrum. And then over there on the bottom left is a delineation of different supernova classifications. You'll see that the way that we classify supernovas is largely dependent on the process that formed them, type 1 versus type 2. And then what we see present in their spectra afterwards. Do they have oxygen or helium or other elements present in their spectra as we observe them? That'll break them down further into, type 1A, type 1B, type 1C, type 2A, type 2B, that sort of thing. And that is down there on the left, all the different light curves that correspond to different types of supernovas. Variability is something that I talked about a little bit before. Over there on the top, again, that is a light curve, a different light curve from Myra. And then there on the bottom is another light curve for Aura Lyrae. Variability this year, we are focusing on 2 broad types of variability. The first one is intrinsic variability, which is variability that occurs within just a star itself. That's the kind of pulsation process that I was describing before with Aura Lyrae. This is something that occurs by a star completely on its own. Nothing else is involved other than the star itself being at that stage of its life where it is pulsating. But you can also have extrinsic variables. Extrinsic variables are things like SS Cygni, which was that white dwarf with the red dwarf companion that I described before, where the variation in the brightness is not one object, one star that is undergoing a fully intrinsic closed system process, but rather there is material entering into the star's own environment because it's part of a binary system. And the accretion of matter, for example, onto the surface of a white dwarf would be an extrinsic binary system. We see an extrinsic variable in a binary system. You would see that there are fluctuations in the brightness of the system because matter falls in, is accreted, produces this big outburst of energy, pushes away some of the other matter. You get a quiescent or low intensity stage, and it remains relatively stable until more matter falls back in, and then it brightens up again, and so on and so forth. So these are the two broad kinds of variability that we're mostly concerned with this year, intrinsic and extrinsic. It's also very important, as I alluded to before, to get used to studying the same object in different wavelengths. Multi-wavelength observation is a very important component of this year's event, as is the case every year, because objects are going to appear differently in different wavelengths depending on what kind of light you're looking for. When you're looking at an object with X-ray imaging, as you would in this picture of Cassiopeia A, the X-ray image is studied by Chandra, and this is for things that are very high energy. X-rays are higher energy than infrared, which is over there on the right, pictured by JWST. X-rays are going to reveal very hot gas. It's going to reveal debris from the supernova, and maybe even a blast wave from the supernova explosion that is still echoing through the structure of the supernova remnant. Very high energy, very bright, very intense events. And then over there on the right is an infrared image. And infrared is generally going to give you lower energy things like emission from dust that is being warmed up because of the hot gas that is around it. So you'll see streaks of dust that maybe give you more structure, maybe show you a bit more about where all the material is distributed. This is going to be the cooler spots within the supernova remnant, the things that are not as high energy. And you can look at the same object in two different wavelengths or more and learn different things about what's going on. You wouldn't be able to see that very, very hot gas in the infrared image. You wouldn't be able to see the glowing emission from the dust that is warmed up in the X-ray image. You have to look at the same object in different wavelengths, usually by different telescopes, in order to get that information. Speaking of different telescopes, as I alluded to, we want students to be familiar with astrophysics missions. All the ones that I talked about are up there at the top, and that would be Hubble with JWST, Swift, the Spitzer Space Telescope, Chandra, the Fermi Space Telescope, and then LIGO down there at the bottom. And in the case of all of these, the main question that we want students to be concerned with answering is, why is it that this observatory was used to inspect or study this aspect of the image being taken? And why was this observatory built to do the kind of science that it is made to be doing? When we design a telescope to look at X-ray images, as in the case of Chandra, why would we want to have a telescope that is designed specifically for high energy events? Why is that something that's important? Why do we need something that is dedicated just to studying those things in that way? Could you use LIGO to take an image of Betelgeuse, for example? Would that be restricted to Hubble? Would that be restricted to JWST? If you wanted to study Cygnus X1, should you do it with the Spitzer Space Telescope, or should you do it with Chandra or the Fermi Space Telescope? These are the sort of questions you should be asking yourself, and you should be familiar with why these missions are set up to do the kind of science that they're set up to do. Because science, as it happens, is the result of whatever tools we have access to, whatever was built and engineered to do the science as it is. And then I'm going to close this up by talking a little bit more about some of the math that we want students to be familiar with, algebraically speaking. Take a drink of water for dramatic effect, because everyone loves math. I want to stress again, before I talk about this in any greater detail, that when I talk about math and physics, what I'm principally concerned with here, and what I want you studying for this event to be concerned with, is how do these quantities relate to one another, and how would a change in one propagate out to a change in the other? If, for example, I took the temperature of a star, which is related to its peak wavelength on a spectrum like this, a blackbody spectrum, if I took its temperature and I cut it in half, what would we expect to happen to its peak wavelength? Would the peak wavelength double? Would it be reduced by half? Would it be reduced by a quarter? Would it quadruple? Would it quintuple? Would it 16-tuple? We know that temperature and peak wavelength are related to each other, and they're related by this over here, which is Wien's displacement law. And then we also know that the radiant flux, which is related to the luminosity and the radius of the star, is also related to its temperature by that Stefan-Boltzmann law right there. So let's say we took the luminosity of a star and we said that we're going to keep the temperature the same, but we're going to double the luminosity. All else being equal, do we expect a increase in the radius of the star, a decrease, and by what factor? These are the sorts of questions, and this is getting onto the more difficult end of this event. No question should be more challenging than if I change this factor, or if I change this quantity by this factor, how would we expect that to change some other factor of the object that we're studying? There should be no calculations. There should be nothing that you can't do in your head. Oh, you doubled it and it's taken to the second power. That means it's going to quadruple the other factor of things as long as everything else is kept equal. Those sorts of questions. So in addition to the Stefan-Boltzmann law, we want students to be familiar with how to measure cosmic distances. If a thing is being observed via parallax, which is the shift in a star's location in the night sky as the Earth completes a circle around the sun. You can kind of approximate this for yourself if you hold your finger out in front of you, close one eye, and then blink to the other eye. You'll see that if you go back and forth quickly, your finger will kind of shift back and forth ever so slightly. You can measure the shift that takes place, and you can use that to determine how far away something is. Bring your finger close to your eye, and when you open and close your eye, you'll see that the shift is very big. There's a big jump here, 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 here for where your finger is. Hold it out very far away, and it's a much smaller jump. It takes up less of your angular vision. And this is an indication that when something is very, very far away, it's going to shift very, very slightly. If something is very close, it's going to shift a lot if you're looking at it from two different vantage points. And then when you're getting out to the point where things are no longer even detectable by their shifts, you might start to look at the distance modulus, which is a comparison of absolute and apparent brightnesses or magnitudes. The absolute magnitude is an intrinsic value, something that has an absolute magnitude of 10 is always going to have an absolute magnitude of 10 no matter where it is. When you move it closer or further from the Earth, however, it'll appear brighter or dimmer, and that's what we call the apparent magnitude. So if something is very, very bright and very, very close, it's going to appear very bright. If something is very, very dim and very, very far away, you're probably not going to be able to see it. But something that's very, very dim and very close might appear to be the same brightness to us as something that's very, very luminous, but very far away. Because the further away something gets, the harder it is to see it. Think about trying to look at a light bulb right up against your face versus a light bulb a mile away. Which one is going to appear brighter? And then the last thing that I want to, I guess not quite the last thing, I have a couple more after this, one more after this. I want to talk a little bit about standard candles, but I'm not going to spend a ton of time on this because I already went over them when I talked about RR Lyrae variables. But again, briefly, standard candles are objects that no matter what kind of object you see it as, if it's an RR Lyrae variable, it's always going to have the same luminosity, which means that if you know what the luminosity is for an RR Lyrae variable, and then you see how bright it is, you already now have two of the three quantities that you need in order to determine how far away it is, because you don't need to do any further analysis to try to figure out what its absolute magnitude is. That's already a known value for RR Lyrae variables, so if you know that, and then you know the apparent magnitude, you can guess the distance. Take that apparent magnitude, double it. How does that affect the distance? If it is suddenly a whole lot brighter, does that mean that it got further or closer? And then vice versa, if you cut it in half, further or closer away. And then the last thing to talk about in orbital mechanics, Kepler's third laws are going to be the main things to cover here, although I did go over a couple other things at the beginning of this presentation, things like Newton's laws of gravitation, that sort of thing. And Kepler's laws are very important for describing objects that are in binary systems or that are in orbit around each other. Things like planets orbiting stars, or very importantly this time around, two stars in orbit around each other. You'll remember when we covered all the DSOs that objects that are in binary systems with each other, compact binary systems, as is the case for Cygnus X1 or for the whole stellar pulsar, or objects that are just two stars in orbit around each other, things like Myra, where it is a A-type star and a white dwarf star. All of these are going to be bound by Kepler's laws, which will relate different quantities to one another. Kepler's first law describes the elliptical structure of how objects orbit each other in space. Kepler's second law describes the areas that are swept out by stars and planets in orbit as they move through their orbit. It causes you to orbit at a faster velocity when you're closer to the thing that you're orbiting, and then at a slower velocity when you're further away. And then Kepler's third law relates the period to the orbital separation between two objects. The further apart two objects are, their semi-major axis is what we call that, then the longer a period it's going to have. It's going to take longer to orbit something if you're further away. And these are just the mathematical concepts that describe the physics of how objects in orbit are going to interact with one another. So that is the content of this webinar. I hope that you found it useful. I'm going to spend a little bit of time talking about resources, but since this is a content webinar, I'm not going to focus too much on resources. Broadly speaking, I have found that studying for this event and studying for other space science events is most effectively done if you split up your research into two broad categories: online resources, things you can find on the internet, and textbook resources. For online resources, I have some of these listed here. There's an link to an OpenStax astronomy textbook, which is just a freely available textbook, at least last time I checked, that gives a good broad overview of principles of astronomy and how objects move through stellar evolution phases and live and die. I would encourage you to use Wikipedia for finding primary sources and for finding images, and then going to the sites that you get that information from in order to study it further. And one of the best ways to do this is to go to the websites of individual missions. So I spent some time in this webinar talking about different missions like JWST and Chandra and Spitzer and LIGO and these different observatories that are focused on studying objects in certain wavelengths. All of these missions have dedicated websites where they post the pictures that they take, oftentimes with blurbs underneath that describe what is actually happening in that picture. So I recommend these for studying objects in particular and for learning a bit more about what's going on in their processes and their construction. And then if you're feeling really ambitious, Google Scholar will allow you to look for published research. Oftentimes, this gets very deep into the weeds of the precise structures of things that are happening. A lot of it is above the B division level, and I would not recommend going to Google Scholar as your first resource. But if you feel like you've really mastered this event, you feel like you really understand stellar evolution, and you want to look into something that's a bit more complicated and a bit more interesting, looking more at the cutting edge of research, Google Scholar is a great place to start. You can find a lot of published research from academic institutions. And then when it comes to textbook resources, I have a couple of recommendations. The first and probably the best that I could recommend is the book Astronomy Today. It has gone through a lot of different editions. We're currently in the 9th edition from its initial publication in 1993. And Astronomy Today is a fantastic textbook. It is what I studied from when I competed in Science Olympiad, when the dinosaurs roamed the earth and all that. And it is a very good, complete overview of how stars change and grow and evolve. If you're able to get access to it, it is very accessible, it's very well written, and it's very clear while not losing any detail without going too deep into the mathematics or some of the more physicsy challenging aspects of astronomy and astrophysics. It's very approachable, but it's also dense with information and very, very useful. And then there are two other books that I listed here. They are concerned mostly with observational astronomy. So there's a really good if you want to practice using star charts, if you want to practice how you study stars in the night sky. These are called The Stars and a Way to See Them by H.A. Ray, and then Space Atlas 2nd Edition, Mapping the Universe and Beyond by James Trefil. That second one, Space Atlas, is actually the one that I use when I am going stargazing and when I'm using my own telescopes to do astronomy, and I really enjoy that one. I think that it's very clear, and it has a lot of good diagrams that actually show how the night sky changes over time and is very good as a resource for that sort of thing. And that brings us to the end. I really hope that this was a useful webinar for you. If you want to reach out to myself or to any of the other supervisors for Reach for the Stars this year, I gave our contact information there by our email addresses. Myself, Aditya, and April are all very excited about this event. We can't wait to spend time writing the event and working to create exams and proctor those exams at different tournaments. We all care very deeply about this event, and we find it really exciting. Hopefully you do too as you compete in this event. We also have up there event updates, materials, and rules clarifications will be given at that soinc.org website. Of course, you'll be able to find this webinar at the Chandra website, and that will have links to other information that you can access for studying there. And I want to leave just with a few quick bullet-pointed notes about the best way to study for this event. Of course, be very familiar with the event description for the content and allowable resources. Do not get DQ'd because you brought in the wrong materials or you left something behind that you should have had. I'd recommend that you use the webinar for an overview of content topics and deep sky objects, but don't just let your research stop there. I would check out the Reach for the Stars resources page at that soinc.org link that's above. Use that to guide your studying and kind of probe your own curiosities to figure out where it can take you next. And then fourth, maybe most importantly, start practicing right now and practice as much as you can. By practicing, I mean things like writing tests for each other, quizzing each other, study objects, and then make flashcards of the different objects and their images to make sure that you can identify them very quickly. Practice describing and teaching to other people on your team how is it that a star begins as a protostar, enters the main sequence, evolves off of the main sequence, and then if it's a high mass star, go through the full process of its evolution until it ends up as a supernova. Make sure that you can describe every step of that process and what are the things that are going to be different depending on if it's a different mass, if it's a hotter star, if it's a greater radius star, if it's more unstable, if it has different elements inside of its interior, that sort of thing. So practice testing each other, practice teaching to each other, and read as much as you can. Follow the things that you find interesting with this event and allow your curiosity to guide you. And of course, if you have any questions, I am more than happy to field them at those email addresses given above. Myself and Aditya and April are all available to chat and answer questions if you need them. And of course, I hope you have a great season. I wish you the best of luck. I'm very excited for this year of Reach for the Stars, and I think that is going to be a really fun one. So good luck to everybody watching. I believe that you all have what you need to make this a great year and to learn a lot about this event and compete and do very, very well. I'm looking forward to getting through this season and seeing where everybody ends up. So take care, and I hope you have a good day. Thank you very much.